Welcome to G Fun Facts Online. What if I told you that right now, all over the world, scientists, governments, and some of the wealthiest people on the planet are locked in a multi-billion-dollar race to build a star on Earth? It sounds like the plot of a blockbuster movie, but this isn't science fiction. This is the story of nuclear fusion, the audacious quest to replicate the power source of the sun, and how it's moving from theoretical physics to the brink of commercial reality. This is the story of a $40 trillion prize, a venture where fortunes will be made and lost in the pursuit of the ultimate energy source. So today, we're deconstructing the dawn of this new sun and the massive gamble being made on our energy future. To understand the sheer excitement and the torrent of investment pouring into nuclear fusion, you first have to grasp its world-changing potential. At its heart, fusion is the process that powers stars. Unlike the nuclear fission we use today, which splits heavy, unstable atoms and leaves behind long-lived radioactive waste, fusion does the opposite. It takes light atoms, usually isotopes of hydrogen called deuterium and tritium, and smashes them together under incredible heat and pressure. This fusion releases an immense amount of energy. The advantages are staggering. First, the fuel. Deuterium can be easily extracted from ordinary seawater, and tritium can be made from lithium, a relatively common element. This means the fuel supply is abundant and virtually inexhaustible. To put it in perspective, a single gram of fusion fuel has the potential to generate as much energy as burning 10 tons of coal. That's enough to power our entire civilization for millennia, freeing us from the volatile politics of fossil fuels. Then there's the environmental angle, which is a total game changer. Fusion reactors produce zero greenhouse gases during operation. The primary byproduct is helium, an inert, harmless gas you put in party balloons. While the reactor components do become radioactive over time, this waste is far less hazardous and has a much shorter lifespan than the waste from fission plants. Many parts could be recycled within a century. And finally, there's safety. The process is inherently safe. There's no risk of a meltdown like at Chernobyl or Fukushima. The conditions needed for fusion, temperatures hotter than the core of the sun, are incredibly difficult to maintain. Any disruption causes the plasma to cool in seconds, and the reaction simply stops. There is no chain reaction. The fuel in the reactor at any one time is only enough for a few seconds of operation. For decades, the public face of this monumental effort has been a project called ITER, the International Thermonuclear Experimental Reactor, being built in France by a consortium of 35 nations. ITER is one of the most ambitious science experiments in history. It's a behemoth, a massive-scale test to prove that we can get more energy out of a fusion reaction than we put in to start it. This is a crucial milestone known as net energy gain. ITER is based on a design called a tokamak, which is essentially a donut-shaped magnetic bottle designed to contain the superheated plasma. But ITER is a story of immense scale and immense challenges. Its budget has ballooned to anywhere between $22 and $65 billion, and its timeline has stretched, with full operations now not expected until 2039. But while ITER has been moving at the pace of international diplomacy, something else has been happening. The fusion landscape has been completely revolutionized by a surge of private investment. We're talking about a Silicon Valley, fail-fast approach to building a star. Over $7 billion in private capital has flooded into the sector, funding more than 50 startups, each with its own unique technology and aggressive timeline. This is where the race gets really interesting. One of the frontrunners is Commonwealth Fusion Systems, or CFS, a spin-off from MIT. They've raised over $2 billion from investors like Bill Gates and Google. Their secret weapon is a new generation of high-temperature superconducting magnets, which allow them to build much smaller, more powerful, and hopefully cheaper tokamaks. They're aiming to demonstrate net energy gain with their Spark project by 2025 and have a commercial power plant online in the early 2030s. Then you have Helion Energy, which made headlines with a landmark deal to sell fusion-generated electricity to Microsoft, aiming to be online by 2028. They use a different, non-tokamak approach they believe is a faster path to commercial power. Another major player is TAE Technologies, which has attracted over $1 billion from Google and Chevron. They're working on a linear design that aims for a type of fusion that produces almost no neutrons, which could dramatically simplify the materials problem. This explosion of private companies, from General Fusion in Canada to Zap Energy in the US, is accelerating innovation at an incredible pace. We're now seeing a powerful synergy where huge public projects like ITER lay the scientific groundwork, while nimble private companies race to commercialize the technology. So building a star is an incredible idea, but it comes with a truly colossal price tag. The single biggest hurdle for fusion energy is the immense upfront capital cost of building a power plant. Estimates for a commercial reactor range wildly, from about $2.7 billion to nearly $10 billion for a single 1,000 megawatt plant. These costs are driven by the sheer complexity of the machines, the powerful magnets, the massive vacuum chambers, and the sophisticated heating and cooling systems. To figure out if fusion can compete, economists use a metric called the levelized cost of energy, or LCOE. This is basically the bottom line price of the electricity it produces over its lifetime. For fusion to win, its LCOE has to be competitive with other sources. Right now, onshore wind and large-scale solar have an LCOE of around $33 to $52 per megawatt hour. Projections for fusion are still speculative, but the target is to get into that same ballpark, maybe around $60 to $70 per megawatt hour after the first few plants are built. Getting there means driving down construction costs through innovation and standardization, and making sure the plants can run reliably for long periods. Beyond the cost of the plant itself, there's the challenge of the supply chain. While the fuel is plentiful, the components are not. We're talking about a whole new industrial ecosystem that needs to be built. We need factories that can mass-produce massive superconducting magnets, advanced materials that don't exist yet in industrial quantities, and systems to handle and breed tritium fuel right inside the reactor. This creates a classic chicken and egg problem. Suppliers are hesitant to scale up production for a market that doesn't fully exist yet. If the promise is so great and the money is pouring in, what are the big roadblocks still standing in our way? The main goal is to create and sustain what's called a burning plasma, a state where the fusion reaction is self-heating, like a fire that keeps itself going. This is incredibly hard. First, you have to contain plasma at over 100 million degrees Celsius. That's 10 times hotter than the core of the sun. The magnetic bottles in tokamaks are good, but the plasma is notoriously unstable and can leak out. Second is the materials problem. What do you build the reactor out of? The inner wall of the machine is bombarded with intense heat and a constant stream of high-energy neutrons. This radiation can make materials brittle and radioactive over time. We need to invent and test new alloys that can survive in this extreme environment for years, and right now, we don't even have facilities that can fully replicate these conditions for testing. As the technology gets closer to reality, a clear and supportive regulatory system becomes crucial. The good news is that governments are starting to recognize that fusion is not fission. In the US, regulators have decided to oversee fusion under a framework similar to what's used for particle accelerators, which is much less burdensome than the rules for traditional nuclear power plants. This provides the certainty that investors need to keep funding the race. Of course, technology and regulation are only part of the puzzle. Public trust is essential. The fusion industry must be transparent, clearly explaining the benefits and the realistic timelines, and making it clear how fusion is fundamentally different and safer than fission. The successful commercialization of fusion would be more than a technological win. It would redraw the geopolitical map. The race is already heating up. especially between the United States, with its powerhouse private sector, and China, which has made fusion a top-down national priority with massive government funding. The nation that commercializes fusion first could achieve true energy independence, fundamentally shifting the global balance of power and limiting the use of energy as a political weapon. And the impact goes far beyond just electricity for the grid. The high-grade heat from fusion reactors could be used to produce clean hydrogen on a massive scale, desalinate seawater to provide fresh water, or power heavy industries like steel and cement manufacturing. It could even lead to advanced propulsion systems for spacecraft, opening up our solar system. So where does this leave us? The journey to a fusion-powered world is a marathon, not a sprint. The challenges, both scientific and economic, are immense. Private companies are aiming for the 2030s to get the first plants on the grid, while more conservative estimates place widespread deployment in the 2050s or beyond. But despite the hurdles, the momentum is undeniable. The combination of urgent climate goals, rapid technological breakthroughs, and a torrent of private investment has lit a fire under this field. The business of creating a star on Earth is a high-risk, high-reward endeavor. It's a testament to human ingenuity and a bold bet on a future powered by clean, abundant, and sustainable energy. The prize is so great that it's a gamble the world is finally, and eagerly, willing to take. Thanks for listening to G Fun Facts Online.